Alright, welcome back. We are doing continuing with chapter 15 on the continuous random variable, and in 15b what we're going to look at is the measure of a mostly measure of the center. I kind of had to split it in two parts in this, which is covered 15b and kind of 15c. But today what we'll look in this session is looking at the mean, the variance, and the standard deviation. Okay, so with do you remember with the calculation of the expected value? I'm just wondering why my slides are so small. Okay, just bear with me. Alright, first let's look at the expected value of x. Alright, just to remember, a reminder, the mean or mu is the integral over the whole domain of x times f of x dx. That x relates to that variable here. So if we apply the expected value of g of x, we're going to substitute that by expected value of g of x. As it is a function, we're going to go lowercase, but all we need to do in the integral is having a factor, which is a new function. Okay, for the variance, do remember that the definition of the variance is the expected value of x squared minus the square of the expected value of x. And by square rooting, we get the standard deviation. Also, as we covering 95% of the variable of that space, okay, within two standard deviation, it's going to be roughly for close to 95% for most of the distributions. It's usually an estimation we're going to get. Most of the curve will kind of have bell-shaped curve. It could be a little bit skewed, but it doesn't really matter as you contain most of the data. Alright, let's look at a question. So here is a probability density function that is defined here. So the function is positive, and the integral of that function over the whole domain is going to be equal to 1. So first determine your expected value. So you define your integral x times f of x, and you, as normal, calculate your integrals. Okay, whoops, so that is 4 over 3. Next step, we need to find the variance. So you need to find first, we have the expected value of x from part A. We need to find the expected value of x squared. So you substitute in here, you write your integral, and you expand that, you anti-differentiate because that's a cubic, that becomes a quartic with the boundaries here, and that simplifies to 2. We express the variance formula, we substitute, we simplified, and then after that we can square root to get a standard deviation, which is the estimation here. Alright, calculate the boundaries within two standard deviation, below and above, and then we just write a statement to explain what it means. So we have our upper boundary here, a lower boundary. Therefore, the probability of the random variable x to be within that value and that upper value, which is written here, is close to 95%. Okay. Yep. Oh, my bad. So with the upper boundary, because the function is 0 over 2, the upper boundary, you need to change that upper boundary of 2.28 to 2 to be the same. Okay. All right. So there is 95% probability that a random variable of x is going to be between 0.39 and 2, not the original 2.28, as our function is defined to be 0 when x is greater than 2. Alright, another application of integration, you could be asked to determine the expected value of a function. So you substitute your e of x and you try to anti-differentiate that. I think you would have to cast it, or you will have to do integration by parts. Then we get this answer. I think I had to do it integration by part, or yeah, use a cas. Okay, and that's gonna be the answer. All right, moving on. The expected value of a function is going to be different of the function of an expected value. So it's the same as when you have a function of a function, the order of the functions will matter. That example is when you square it. So we know the e of x squared is not the same as the square of the expected value of x. The exception is when you apply a linear function, so in the form of ax plus b to a random variable, and we can determine the expected value and the variance using those rules. So we've seen that before. Okay. All right. Side note. So let's say you have a function associated with a random variable x. You can transform that variable x linearly. You will generate a new probability density function. Okay. Before you do that, what's important is link it to the transformation mapping. So let's go back to the beginning of the year when you did transformation. So your x has to become ax plus b, which is fine. Now when you multiply by a, let's say a is greater than 1, your domain will become bigger. Okay, just think about it. So your domain becomes bigger. It means that your area under the curve might increase. Now remember, for probability density function, that area is always equal to 1. So at the same time, on the y variable, we need to make it smaller. So there's a dilation of factor 1 over a, and what will happen is that new function will still have an area of 1 under the curve, so it will still be a probability density function. So by combining those two transformations, that new function will be, we do that transformation, it has to do with the mapping. So that's my x prime, that's my y prime. We substitute and make x and y the subject, and that will give you the transformation for x. And on the right hand side, you would be, that is my g, and it will sorry, that's gonna be my g, and that needs to be equal to y, and when you y is my f. So by making g the subject, we multiply by 1 over a. Okay, I hope that makes sense. Anyway, so this is the way we follow that transformation. We're gonna use that later when we do a normalization of normal distribution. Okay, and a lot of new terms, so bear with me. All right, this part is kind of there's a proofing in 15D which is optional, but you need to keep that information in mind as it links back to transformations. All right, let's moving on. You have a linear equation of a random variable. We know the mean, we know the variance, therefore the standard deviation. we can determine the expected value using, if I go back to some previous slides, those are the relations or the rules that we're going to use to determine the expected value and the variance after the linear function. Alright, so we apply that. We do the same with the variance, so it's a new linear function. So what matters is the scale factor, which we apply here. Alright, now you have a rule. So find the rule for the probability density function g in the term f for 2x plus 1. So that's your a and that's your b. So you write your function g, and that is equal to 1 over a. We use the rule and we substitute the value of a and b, and we get the new function g in terms of f. And that summarizes what we do covering today. Continue to in the next session with the measure of the spread, range, and interquartile range. Until next time.